All right, everybody. This is the last lesson that we're going to do for the entire year, so let's make it a good one. Geometric sequences and series is the topic, and now that we're more familiar with a sequence and series and the difference between the two, we'll focus more on what it means for it to be geometric. So, for example, this is an example of a geometric sequence, because it's a sequence of numbers that you can multiply by 2 each time to get the next term. So if you take 2 times 2, you get 4. 4 times 2 is 8. 8 times 2 is 16. You keep doubling the number to get the next number. That's what it means for it to be geometric. Okay? In series form, this would be 2 plus 4 plus 8 plus 16. Okay, so this is a geometric series because, again, each term gets doubled, so it's got a common ratio, and you're adding each term in the sequence, so that's what makes it a series. Okay, so now the general rule, I can actually prove to you where it comes from real quick. Let's say the first term is a sub 1, as usual. So let the first term equal a1. So then first term is a1. And then let's say, like here, we kept doubling each term to get the next one. Let's call that factor r. So take a1 times r to get the next term. Take this term times r to get the term after. Take this third term times r again to get the one after that. And you start to see a pattern. The nth term, so this is the general rule for a geometric sequence, is always the first term. You see how each term's got a1 in the formula, times r, and if you notice, the second term has 1r, the third term has r squared, the fourth term has r to the third, the fifth term would have r to the fourth, the nth term would have 1 less. So the exponent is r to the n minus 1. So this is your general rule for a geometric sequence. Okay, and that's, for now, that's really all you need to know. I mean, some of these you can kind of do fairly quickly in your heads or on the calculator. Sometimes you have to kind of work with the formula as we did with arithmetic sequences and series. Okay, so here's the first example. Find the second term You know what? Let me go back just a second. I forgot to define what a common ratio is. The common ratio, that's r, and that's kind of like the doubling factor here, but it's not necessarily doubling each time. It's whatever it is in each scenario. And you can find it by just taking any term and dividing it by the term before. So if you look at term 2 here and divide it by term 1, you see how you get r, right? If you take the third term and divide it by the second term, you get a1r squared over a1r. Again, you get r. So the general rule for the common ratio is that you just take any term divided by the one before it. So we use the notation a sub n plus 1, a sub n. So if a sub n is any term, then in the numerator would be the term after. So third term divided by second term. Second term divided by first term. Anything like that would be fine. Okay, so now that we've gotten that out of the way, sorry about that. With these two formulas, you should be able to pretty much solve anything that's involving a geometric sequence. Okay, so for example, if we want to find the second term, with a positive common ratio if A1 is 4 and A3 is 20, well, there's a few things we can do. So if I write it out, this is probably the easiest way to do this one. Obviously, this sequence continues, but we have to multiply 4 by something to get x, and then multiply x by something to get 20. Or, if you take x divided by 4, that should be the common ratio. I should also be able to take 20 divided by x to get that same common ratio. So what that leaves for us then is a proportion. Since x over 4 has to be the same as 20 over x, second term divided by first term, third term divided by second term has to give you that same ratio. You can set these equal to each other and find the second term just by cross multiplying, taking the square root. And since we are told that the ratio is positive from term to term, then we know the second term is also going to be positive. So there's our answer. Okay? And now if you wanted to figure out what is that common ratio, you can take 4 root 5, which is our second term, and you should be able to divide it by 4, and your common ratio is 5. Okay? Or I'm sorry, not 5, it's root 5. Which makes sense. 4 times root 5 is 4 root 5. If we take our second term times root 5, we get a 5 times 4, which is 20, and we're good to go. Okay, so there's one example of a geometric sequence. Let's see. We'll do one more, just so you guys get an idea of how to work with the formula. Find the 8th term in the geometric sequence (3, 2, 4/3, and so on. Okay. Anytime they're asking you for a specific term, the most straightforward way to do this is to go ahead and find what the general rule is. Okay, so find the general rule. Well, we know the general rule for a geometric sequence is A1 times the common ratio to the n minus 1. And in this case, we know that our first term is 3. So it's going to be A sub n times 3. And if we look to find r, probably the easiest thing to do would be to take second term divided by first term. And you get 2/3. If you wanted to do third term divided by second term, you still get 2/3. But why would you do this one when you can just take 2 over 3 and be done with it? So the common ratio, r, is 2/3, and that's to the n minus 1 power. So there's our rule. And now if I'm looking for the 8th term, then all you do is plug in 8 into the exponent. So this becomes 3 to the 2/3 to the 7th power, which if you go ahead and type in the calculator or do it by hand, you get 64 over 243. So this would be the 8th term in this geometric sequence. Okay? So important note, this geometric sequence was increasing. It was doubling each time. 2, 4, 8, 16, right? This is another geometric sequence. Notice, though, that it's going down. 3, 2, 4/3, and so on, and it gets smaller and smaller each term that we go. Okay, and that's actually what's going to help us determine what kind of sums or series we're going to calculate. Okay, so I'm not going to spend all the time deriving the formulas. I will just tell you what the two formulas are. So for geometric series, which again means sums, right? You have two options. The sum of the first n terms, that's what this notation means, can be found by taking first term times 1 minus r to the n power all over 1 minus r. Okay? So this is one option. This is only used for a finite series. Okay? So you're never going to be asked to find the sum of an infinite series using this formula. Okay? But this formula will help you for a finite series. So certainly the 2, 4, 8, 16 example, 2 plus 4 plus 8 plus 16, we could do by hand. We could also plug it into this formula. But this is more useful for geometric series where we have a lot of terms and we don't necessarily want to add them all up. Okay? The second option is for an infinite series. You simply take a1 over 1 minus r. Okay, so there are two things that you need to be careful with this formula. It needs to be an infinite series, number one, and the terms need to be decreasing. Okay, and again, if you think of the 2, 4, 8, 16 example, if you look at those numbers, there's no end to that sequence, but we do know that when you keep adding 2, 4, 8, 16, and 32, and 64, there's no way that you can find an actual sum for that. I mean, eventually that thing's going to go to infinity because each number you add gets bigger, so the sum itself gets bigger and bigger, so it doesn't really have a sum. We say that it just goes to infinity. Now, something like this one, 3, 2, 4 thirds, you see that each term is getting smaller. Okay, or I can do another example, a very easy one. 1 plus 1/2 plus 1/4 plus 1/8, where each term keeps getting cut in half. You can see that as you type in more and more of these in your calculator, that, yeah, the answer gets bigger, but it gets bigger slower. Okay, so 1 is by itself is 1. Add a half, we get 1.5. Add a quarter, now we get 1.75. Add an eighth, now we get 1.8 something. Sorry, I don't have 1.825 maybe. I don't have my calculator with me. But you get the idea. The more and more of these that you add, the bigger it gets, but it seems to be slowing down as you do it, okay? So actually it will converge, is the fancy word, to an actual answer, and this is how we calculate it. Okay? Now, let's do a few of these examples, and then we are done. Find the sum of the first, let's say, 10 terms of 12 plus 36 plus etc. Okay, so all we need to find the sum of the first 10 terms is first term r to the n, which is 10 in this case, minus 1. Oh, sorry, using the wrong formula. That's not what I meant to do. We want to take first term times 1 minus r to the n, which is 10, over 1 minus r. Okay, so this is the formula that we're going to use, and it's not too hard to see that the first term is 12. And the ratio, if you take second term divided by first term, 36 divided by 12 is 3. So that's your ratio. Let's plug it in. And at this point, once you set it up, type this all in the calculator and you get your answer of 354,288, I believe. Okay, so these get pretty big pretty quickly if they're increasing. And this is how to work with the formula for a geometric series where you're just adding up a few of these examples, or a few of these terms. Here's another one. Let's say we have the sum from k equals 1 to 10 of 12 times 3 to the k minus 1. Okay, two things. One, if you don't recognize it, I would always recommend plugging in the first couple of numbers to see what this looks like. So if you plug in 1, 3 to the 0 becomes just 1, and then you get 12. Plus, if you plug in k equals 2 now, you get 3 to the 1, which is 3. 3 times 12 is 36. And oh look, it's the same problem from before. The reason I wanted to show you this example is that you should be able to figure out that this is a geometric series just based on this, because it looks like you have a number, a constant, times a ratio, and then look at the exponent, k minus 1. So it's the same formula for our rule for a geometric sequence. So if you recognize that it's got that pattern, I mean, you can go straight to the formula above and then do everything that's the same. Okay? All right, last example. Let's say we have the sum from k equals 1 to infinity of 34 to the 1/2, or I'm sorry, 34 times 1/2 to the k minus 1. All right, so again, it's got that pattern that it did before. And if you don't know what to do, I mean, you can start writing out the first few terms. Plug in 1. You get 0 for the exponent, so you just get 34. Plug in 2, you get half times 34, which is 17, and so on. This is a decreasing geometric sequence. It's an infinite geometric sequence because we're just going to infinity here. So we're going to use the other formula, which says that all we need is first term over 1 minus the ratio, which we have. The first term is right here. It's 34. 1 minus the ratio is right here in the formula. You get 1/2. If you didn't catch that, you could also do 17 over 34 or 8.5 over 17. You still get 1/2. Okay, and either do this by hand or type it in the calculator. Your answer is going to be 68. Okay, and if you don't believe me, you can write out the first, 10 or 20 of these, 34, 17, 8.5, 4 1/4, and keep adding more and more. You're going to see that it's going to get closer and closer to 68. So we say that eventually, as we add an infinite number of these numbers that are getting smaller and smaller, the answer is in fact 68. And this is how we find it, just using this formula, a1 over 1 minus r. Okay, so that wraps up the unit. The rest is up to you. Farewell, see you in class, ask questions, prepare, and get ready for that last exam.